Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Azim from Group L, and today I will be presenting assignment CFD for Fluid Mechanics 2. We were given a topic of flow and heat transfer in corrugated pipe. Our team member consists of 4 people. Our team leader is Ahmad Hanis Bukhari bin Zainuddin. Team member 1 is Muhammad Irfan bin Zulkifli, team member 2 Syahiratul Maisara binti Zabri, and team member 3 is Muhammad Azim bin Kamsani. All 4 team members have their own tasks that were allocated to them. As for the leader, Ahmad Hanis Bukhari, he will lead the team, divide all the tasks for the group members, and preparing the slide for the presentation. As well as Syahiratul Maisara, she will also be preparing the slides for the presentation, and Muhammad Irfan will be creating NC's Fluent, and for Muhammad Azim, which is me, will be the presenter and creating the video presentation. This is the introduction about the flow and heat transfer in corrugated pipe. The use of corrugated tubes is an effective method in intensification of heat transfer in tubular heat exchangers, but there is currently no universal method of calculation and design of such heat exchangers. Heat transfer between different fluids is used in a variety of sectors. This transfer takes place in a variety of heat exchangers depending on the operating condition and industrial application, such as steam generation and condensation in power and cogeneration plants, the automobile industry, and cooling and heating in the pharmaceutical, chemical, and agricultural thermal processing. The difficulty that drives this work is that these heat exchangers are still quite massive and heavy. It is necessary to shift the flow from laminar to tubular in order to maximize heat exchangers and minimize their surfaces and weight. Enhancing the heat transfer coefficient with the least amount of pressure loss is critical in constructing heat exchangers that meet the goal of high efficiency and low cost while being as small as light and possible. While the regular cavity or ducts of standard smooth pipes, whether circular or rectangular, are well known and represented in heat transfer correlation, this is not the case for corrugated pipe. Despite their better heat transmission in heat exchanger design, this is attributed to the imperfections in the geometry which cause turbulence and improve their heat transfer. So, one promising method is to use corrugated walls, which have a significant effect on the heat transfer enhancement by breaking and destabilizing the thermal boundary layer. In consequence, corrugated surfaces operate as turbulence promoters to enhance heat transfer. So moving on to part 2, which is the theory related with our topic. Heat exchangers are major elements in the industrial power system. It is a large set of heat power equipment with significant industrial applications, accounting for 20% or more of the total cost of equipment used in thermal power, chemical, refining, and food processing. Other industries include the processing sector, utilities, and others. The goal of the modern heat exchange equipment development is complex and varied. Expanding efforts focus on heat exchange intensification, reducing the weight and dimension of heat exchangers, and boosting their productivity is required to reduce energy and material consumption while also lowering heat exchange equipment costs. Today, true rationalization of heat exchanger design is thought to be nearly exhausted. The scientific work of foreign and native scientists are constantly studied for search of method of heat exchange intensification. Passive heat exchange intensification technologies and the usage of developed heat exchange surfaces are now frequently used. No universal method and no criteria are developed for efficiency assessment of the heat exchange surfaces. In order to establish heat general dependencies for calculating the thermal and hydraulic characteristics and evaluating the efficiency, more in-depth investigation of the thermal and hydrodynamic processes occurring in the produced heat exchange surfaces is required. Today, a number of domestic enterprises manufacture thin-wall corrugated flexible stainless steel tubes in various variants. These tubes are inexpensive and widely used in hot and cold water distribution system heating system, and gas-consuming equipment. In addition, the corrugated tubes are resistant to defrosting and water stress, compensate for linear expansion, and can withstand temperatures up to 150 degrees Celsius and pressure of up to 25 kg per centimeter squared. Because of their corrosion resistance and high tube strength, these tubes have long service life and are characterized as reliability and resilience to external and internal mechanical and hydraulic loads due to their material qualities, which also include great flexibility and elasticity. The use of corrugated tubes of various modifications is the effective way to improve the thermal and hydraulic characteristics of heat exchangers. The corrugated tubes create turbulence near to the tube's wall surface, reducing the thermal boundary layer thickness because of the disconnected disturbance from the tube wall to the mainstream. The liquid near the tube wall combines better, increasing the total heat transfer coefficient of the heat exchange systems. So for part 3, which is the objective, this part will be the explanation about the problem that needs to be solved in the simulation. In this assignment, it has been shown that how one can create dimple pipe geometry in ANSYS. Flow and heat transfer in a dimple pipe has been analyzed in the simulation. From this assignment, we will learn how to create dimple pipe geometry in ANSYS, how to mesh a dimple pipe in ANSYS workbench, how to set boundary condition for dimple pipe geometry, and how to define fluid, solid, and solid cell zone in ANSYS Fluent. Also, how to set a residual for convergence, and last but not least is how to obtain post-processing contours plots in CFD post-processing. Part 4, which is the geometry detail and dimensions. So this is the dimple pipe, the front view, the upper view, and the isometric view. Dimension details for the dimple pipe is the outer diameter is 60 mm, inner diameter is 50 mm, offset of 10 mm. Pipe length is 110 mm, diameter hemisphere inside the pipe is 5 mm. The material for the pipe is steel, and the fluid material is of course water or liquid. Part 5 is the simulation method for the inlet, outlet, boundary, and meshing node. For the inlet, after complete creating dimple pipe in mesh pipe, select one of the surface on fluid domain to choose as inlet pipe. The reason to choose it is because it needs to declare the intake of flow in pipe and analyze the behavior of the flow during when the water come into the pipe. For the outlet, the intake pipe was chosen. Other side of the fluid domain was chosen as outlet pipe on this pipe. This need to be considered because the analysis the behavior of flow during the water when the water come out of the pipe. So for the boundary, we have the dimple pipe, pipe wall, fluid domain, and pipe. So this is the dimple. Select one of the dimple and drag copy to all dimple on the pipe. The reason why to declare it because all dimple can effect some turbulence on fluid flow on the pipe. Next one, we have the pipe wall. Select the pipe wall inside the pipe because when fluid inside the pipe have a close contact to the flow, which can effect some friction on it. This is the fluid domain, the part that fluid flow through it. And the next one is of course the pipe, function as a main support for fluid that go through it. So this is the meshing node pipe. Use default mesh by click generate mesh and let the ANSYS analyze it. Mesh is used to check the accuracy of the analysis. More mesh spotted on the specimen, higher accuracy of analysis that can be get from it. So part 6 will be the result. So we can see here the contour 1. Contour 1 represents the behavior of fluid flow in terms of temperature. The temperature was set at 310 Kelvin from the observation. The specimen data shows the temperature of the fluid flow is between 306 Kelvin to 313 Kelvin. So you can see here the contour 1. For the next, we have the contour 2. The contour 2 represents the temperature occur when fluid is flowing into the pipe and output flow. The inlet part mostly flow at the same temperature for all surfaces, which is 300 Kelvin, and the outlet part has various temperature on the surface. The temperature is in between 300 Kelvin to 312 Kelvin. Also as well, we can see in the picture here the temperature. Okay, for the contour 3 represents the velocity of flow through the pipe. We can see from the picture of the streamline, and we can see the zone name, which is the inlet. Velocity specification method is the magnitude, normal to boundary, reference frame is absolute, and velocity magnitude is 0.001 meter per second. The streamline is shown in this picture. The streamline represents the behavior of flow condition and the form of flow when entering the pipe. So this is the streamline vector 1. Streamline vector is representing the flow when entering the pipe. The streamline shows the behavior of the flow when hitting the dimple and not hitting the dimple pipe, as you can see from the picture here. And for the last part, which is the discussion relating to our result and theory. Effect of corrugated parameters on velocity and thermal distribution. The corrugated wall has a considerable impact on the velocity streamline gradient, with a secondary vortex created at the center of each corrugation parameter, according to the findings. The velocity streamline increased and decreased with a change of corrugation parameter. Furthermore, the amplitude, height, and wavelength decrease, the intensity of the secondary vortex increases. The lowest wall temperature, which refers to the effectiveness of the corrugation to reduce the thermal boundary layer thickness and accordingly increases the heat transfer. The wall zone is characterized by a multi-layer temperature gradient due to the high flow mixing and turbulence induced by the corrugation interruptions. Next, we have the effect of corrugated parameters on the heat transfer and friction factor. Because of the increased pressure drops and surface area created by the corrugated wall, the friction factor has increased. Furthermore, the Nusselt number increases with the increase of Reynolds number because of the number of vortexes will increase and the thermal boundary layer becomes thinner. This augmentation in the NU is due to the boost in the fluid mixing in the downstream section, and the better temperature gradient as the amplitude height increases. And that brings us to the end. I'm from Group L would like to thank you for your time and attention.